Have you ever stopped to think about what's actually happening when you cook? I mean, really happening on a scientific level. Well, today we're diving into the fascinating science that's totally transforming how we understand food, taking us from the kitchen stove right into the classroom. So to get us started, let me ask you a question. What could mayonnaise, a light, fluffy meringue, and, say, a wobbly block of Jell-O possibly have in common? I mean, on the surface, they're completely different. One's a creamy spread, one's an airy cookie, and one's, well, jiggly. But believe it or not, there's a deep scientific connection hiding in plain sight. And the answer is a field of physics called soft matter. Yep, physics. This is the science that explains how these everyday foods get their unique textures. And it's the very same science that chefs use to create mind-bending dishes, like turning liquids into these little flavor-packed spheres that just explode in your mouth. All right, here's the game plan for today. We're going to start with the basic science happening right on your plate. Then we'll get into the three key players: emulsions, foams, and gels. After that, we'll look at the culinary revolution this all sparked, see how it's being taught at Harvard, and finally, we'll wrap up by showing you how your own kitchen is the perfect lab. Okay, let's kick things off with a big idea here. Every time you whisk an egg, whip some cream, or even just dissolve gelatin in water, you're not just cooking, you are, quite literally, running a physics experiment. The specific science we're talking about is soft matter physics. It's a field that studies materials that are, well, soft. They're things that change their shape really easily when you heat them up or push them around. And when you think about it, that describes almost all the food we work with, right? It's the science of all things squishy, stretchy, and gooey. Now, within this world of soft matter, there are three structures that are absolutely fundamental to cooking. You can think of them as the three culinary cousins: emulsions, foams, and gels. They're all part of a bigger family called colloids, which are basically just mixtures where one thing is suspended inside another. So first up, we have emulsions. This happens when you take two liquids that normally refuse to mix, like oil and water, and you force them to get along. A simple salad dressing is an emulsion, but it's a temporary one. Mayonnaise, on the other hand, is the real deal. It's a stable emulsion where tiny little droplets of oil are suspended in a water-based liquid, all held together by a peacemaker, an emulsifier, like the lecithin in an egg yolk. Next up, foams. A foam is simply a gas, usually just air, that's been trapped inside a liquid or a solid. The classic example is whipped cream. When you start whipping, you're basically building a delicate cage made of fat and protein that traps countless tiny air bubbles. And just like that, you turn a simple liquid into something light, airy, and delicious. And last but not least, we have the weirdest of the bunch: gels. A gel is a liquid that's been suspended inside a solid structure. Think about it. Long, tangled protein chains, like gelatin, form a microscopic mesh, like a net, that traps water molecules. That's how something like Jell-O can be almost entirely water, but still hold its shape and jiggle like a solid. So let's just quickly recap that. It's actually pretty simple when you break it down. An emulsion is a liquid inside another liquid. A foam is a gas inside a liquid. And a gel is a liquid trapped inside a solid. It's this basic framework that gives us everything from creamy vinaigrettes to light-as-air meringues and wobbly jellies. So you might be wondering, when did all this science stuff officially make its way into the kitchen? Well, that brings us to a movement that completely flipped the world of fine dining on its head: molecular gastronomy. The whole spirit of this movement was captured perfectly by the physicist Nicholas Curti way back in 1969. He had this fantastic quote where he basically said, "Isn't it kind of crazy that we can measure the temperature on Venus, but we have no idea what's actually happening inside a soufflé as it rises?" He believed the kitchen was a laboratory just waiting to be explored. And it all became official in 1988 when Curti and a French chemist named Hervé Thys finally gave it a name. Then, in 1992, they held the first of many workshops in Italy, bringing top-tier scientists and world-renowned chefs into the same room to talk, experiment, and learn from each other. And by the 2000s, chefs like Ferran Adrià and Heston Blumenthal had taken these ideas and launched a global food phenomenon. But here's a funny thing. A lot of the chefs who became famous for this style of cooking actually hate the name molecular gastronomy. They feel it sounds cold, way too scientific, and frankly, a little unappetizing. So over the years, other names have popped up, like modernist cuisine or avant-garde cuisine. Chef Ferran Adrià even called it techno-emotional cuisine because he felt it better captured the blend of technology, art, and pure feeling that went into his food.
But this revolution didn't just stay in those fancy Michelin-starred restaurants. It also started making its way into the classroom, and nowhere more famously than at Harvard University.
At Harvard, they created this amazing course called Science and Cooking, and its whole purpose is to use delicious, hands-on food experiments to teach really fundamental physics concepts, especially to students who might normally run screaming from a physics class. A huge part of the course is about translating our everyday experience of food into the language of science. For instance, when we talk about a steak being tender or tough, what chefs call mouthfeel, a physicist describes that exact same quality with a single number. It's elasticity. So each week, they'll introduce an equation of the week. And for elasticity, this is it. Now hold on, don't let the letters scare you. You don't need to solve it. The whole point is to understand the relationship. E on the left stands for elasticity, how tough the food is. And the most important part for us is that little L on the other side, because L represents the tiny, microscopic distance between the protein strands in your food. So think about cooking a steak. As it heats up, the proteins tighten and pull closer together. That means L gets smaller. And because L is in the denominator of the equation, when it gets smaller, the elasticity, E, gets much, much bigger. And that right there is the physics of why a well-done steak is tougher than a rare one. It's that simple. And of course, the best part is the labs, because they're completely edible. In this experiment, students are actually measuring how heat moves through a chocolate lava cake while it's baking. By understanding the physics of heat diffusion, they can calculate the perfect time to pull it from the oven so the outside is perfectly baked, but the center is still that gloriously molten chocolate. It's science you can actually eat. Okay, so this brings us to our last and maybe most important question. What does all of this mean for you, for the everyday home cook? Someone on Reddit actually asked this very question about the online version of the Harvard course. They wanted to know if it was worth paying for the certificate, like what was the real-world value? And people who had taken it all chimed in, saying the real value wasn't some piece of paper. It was a whole new way of thinking about food. And that is the absolute key. Once you understand why a recipe tells you to do something, why you have to whip egg whites in a clean bowl, or why an emulsion sometimes breaks, you're no longer just a robot following instructions. You're in control. Cooking stops being about following steps and starts being a creative, problem-solving process. So, the next time you step into your kitchen, just remember this. It's not just a kitchen. It's your own personal laboratory. Every meal is a chance for a new discovery. So the only question is, what delicious experiment are you going to run next?